G'day and welcome to the first video on continuous random variables, exercise 9.1 in your textbook. So in this video I'm just going to briefly describe the difference between continuous random variables and discrete random variables, and then I'll show you some examples of continuous random variables. So essentially the difference is that discrete random variables, this is chapter 8 in your textbook, these distributions can commonly be counted and are separate, distinct entities. So, for example, the number of people in Year 12 classes, or the number of red lights while driving, or the number of red cards in a card game, for instance. As opposed to the continuous random variables, which is chapter 9, these distributions, it's all about probability. These ones are commonly measured by the category, and the categories merge with one another. So while these ones are distinct, like you can't get 2.5 people or 6.5 red lights. You've either got 6 or 7. In continuous random variables, you can actually kind of get the boundaries get a bit muddy, or the categories get sort of merge with each other. For example, time spent doing homework last night, was it 1 minute or 1.1 minutes or 1.09 minutes or 1.089 minutes, and so on and so forth. You can get seconds and then microseconds and like even tenths of microseconds and all that sort of thing. Or for example, the length of a fish in a river. You can get 1 meter fish, that'd be a big fish. You can get 50 centimeters, you can get 51 centimeters, you can get 51.1 centimeters, and so on and so forth. And weights of apples in a tree. These could all be continuous random variables here. And so that's briefly the difference between the two. To be honest, you probably don't need to know a lot more about that. You just need to be able to identify if it's a continuous or a discrete, and then apply the following formulas. So in chapter 9, we'll be dealing with continuous random variables, and that's what I'll go on with now. Okay, so imagine this situation. We're sitting in class during period 1 and 2, and we know that there will be a fire drill at some point in this class. We don't know when it will happen, except that it is guaranteed to happen during this class. We want to have some idea of the time of this event, and so we are told that the time is modelled by the probability density function, or PDF for short. 3x multiplied by 100 minus x, all over 25 million, where x is the time in minutes from the start of the class. Okay, and I probably should put at this point that I should put the boundaries of this. I should put the domain. The domain is from 0 up to the end of our class, which is actually going to be 100 minutes. Every other point is equal to 0, and I probably should write that a little bit better. I might do that a bit later. So probability density functions, these functions enable us to find the probability of continuous events occurring. There are two conditions for PDFs. I'll show you what they are. So PDFs are basically, that's what continuous random variables are. So probability density functions, there's two conditions, and one of them is that all of the graph needs to be above 0, above the x-axis basically, for the relevant domain. So for this graph here, it has to all be above the x-axis between 0 and 100. Or it can be on the x-axis as well, I should mention that. It doesn't matter what happens outside of that domain, but for that domain it must be all above the x-axis. And the other thing is that the area between the two boundaries, so in this case from 0 to 100, must equal to 1. A and B are the relevant domain. So when we integrate between A and B, it must equal 1. Those are the two conditions for a PDF. And if it's a PDF, then it can tell us about probability, and we can work out probability and all that sort of thing. If it's not a PDF, then we can't go any further. Okay, so this is a sketch of the graph that we were looking at before. This is f of x, and so it looks like 0, 0 is one x-intercept, and the other x-intercept is I think it's actually 100. That 109 is actually the end of the graph over here, but the x-intercept is actually 100. Okay, so that means that the start of the class and the end of the class. And if I do the area between 0 and 100, I should get the answer of 1, and I might just do that just to prove it to you. Lucky I did check this. I've made small mistakes, actually probably a big one. That should be x squared. So 3x squared times 100 minus x. And now if I do this, if I I'm going to define it on my calculator there, and if I integrate between 0 and 100, I get the answer of 1, which means that it is a PDF, and so therefore I can start using this graph for probability. So that's what I'll do in the next video. I'll use this graph, this function, and this situation to work out all sorts of different things and find out when this fire bell is actually going to go. So thanks for watching, and make sure you watch the next one.